And the topic I will be covering is engineering application of artificial intelligence. Very quickly, I'm a professor at petroleum engineering in West Virginia University, and I have started what today is called artificial intelligence. I started my research in that in 1991. And since then, I haven't done anything that had nothing to do with what today is called AI. And I explain what I mean by saying what today is called artificial intelligence. But anyways, let me go ahead and share my screen and start my presentation. Can you please let me know if you can see my...
Yes, we can see the presentation.
Very good. Thank you so much. The outline will be, I'm going to have a very, very brief, only 3-4 slides, history of AI. And I'm going to provide some definitions of AI. Recently, I have learned that in engineering, there are a lot of different definitions of what really actual definition of AI is by those who created AI rather than by those who are using it. Then I will be talking about modeling physics using artificial intelligence and machine learning. Then what I mean by, or what is engineering application of this technology. Then one of the key issues that I have been coming across a lot is a lot of engineers and even non-engineers think that traditional statistics is very similar or is the same as artificial intelligence and machine learning because they both using data. Well, I'm going to explain why these two are completely different from each other. However, as an AI person, you need to learn and know traditional statistics, but they're not the same. And I'll explain that, how, why. And then in the context of all of that, I will talk about smart proxy modeling, which is one of the major applications of AI in engineering. There are two of them. One is smart proxy and one is direct modeling using data, real data. And the difference, it's very hard to talk about it in a short period of time. I'm going to mention it, and if there is a question, I can go in as much detail as you're interested. And finally, if time allows, I'm going to provide you with a case study. And that case study is using AI to deal with computational fluid dynamics in a mechanical chemical engineering application to show you what AI can do. So let's start with the brief history of artificial intelligence. It all goes back to Alan Turing. He was an English mathematician, computer scientist, biologist. Goes back to during the Second World War in the US. He's known as father of modern computing. He was a brilliant mathematician and logician. And he developed the idea of modern computer and artificial intelligence back in 1950s. And of course, again, because it's very, very brief, I can show you the people such as John McCarthy, McCulloch, Pitts, Rosenblatt, Widrow, and Hoff. These are people that played a big role in artificial intelligence a long time ago. However, and one more thing that's very important to mention is the original version of artificial intelligence was using data and rules. In the data, it was using what's today's called artificial neural network, but it's a very different version. I'm going to talk about that. And of course, they were using rules, and it was called expert system. And these rules uses Aristotelian logic. So what happened in 1969, two professors, MINSKY and PAPERT, they published a paper, a book actually called PERCEPTRON, providing the limitation of two layers feed-forward neural network that I said they were using artificial neural network at the beginning. And they proved that the current version that is being used is not working well. It can only solve linear problem, not linear problems, and that became a big deal actually. This book impacted the limitation of research funding on data-driven artificial intelligence, and literally data went out and everything became rules-based. So at that point forward, whenever anybody was saying artificial intelligence, they meant expert system, and incredible amount of research grant went to that until 1986, which is after 2 decades. A backpropagation algorithm for neural networks solved the problem that was mentioned by those two professors on their book, PERCEPTRON. And what happened, the backpropagation algorithm incorporated and developed solution for multi-layer, not 2 layers, and feed forward and backward, feed backward and forward both for the neural network. They changed everything at that point, and that changed everything, literally. Now data came back to what's today is called artificial intelligence. After backpropagation algorithm, the term artificial intelligence was avoided. Why? Because what expert system was doing was unsuccessful, and people did not want to say this is the same thing. That is why the terms from 1986 to about 2000, the terms that they were used for this technology was called virtual intelligence, intelligence system, computational intelligence, soft computing, and so forth. So literally, at that point, rules went away and everything became data related. And when the rules went away, the artificial intelligence did not solve. Why did rules went away? Because artificial intelligence, what was called artificial intelligence through expert systems, did not solve any actual problem for decades, even using tens of millions of dollars of research funding. However, now, the new version of the artificial neural network came, fuzzy set theory came, evolutionary computing came. That was the artificial intelligence. But again, as I said, it was not used on that terminology until 2004, 2005, after what Google did in image recognition. Then the term artificial intelligence came back. And now that we're calling artificial intelligence, it's all about data and those algorithms. So what is the definition of AI and machine learning? We go back to 70,000 years ago when cognitive revolution started by Homo sapiens coming to what today is called Asia and Europe. And there's a detail we can go through it, why it's called cognitive revolution, what is the difference between Homo sapiens and Neanderthals and Homo erectus, and that's why it changed a lot of things. And they were around for hundreds of thousands out of Africa. But anyways, so 70,000 years ago, the Homo sapiens came, and then 12,000 years ago, they changed a lot of things through agricultural revolution. And in mid-18th century, there was another revolution, was industrial revolution, which we are familiar with as engineering that we're talking about today to a very large extent has to do with that. And now we are going to have a new revolution. It started in mid-1980s, and there are these revolution has two characteristics. One is what AI is, and the other one is biotechnology, which I can go into the detail of that. I'm sure you've probably heard of CRISPR-Cas9. And these two is going to change a lot of things. Now, when, how, that's not something I'm talking about right now, because we're talking about the engineering application of that. So let's first identify the definition of AI and machine learning. This is the definition that I didn't make, of course. This is the definition of AI for those who created this technology. Artificial intelligence is the technology that simulates human intelligence. How? It does it by mimicking human brain. in order to analyze, model, and make decisions. That's literally the simple but a realistic identification of, or definition of what artificial intelligence is. What is the definition of machine learning? Unfortunately, a lot of people today even call linear regression, they call it machine learning. Is that true? Well, what is machine learning? Machine learning is the science of making computers to act without being explicitly programmed. Folks, numerical reservoir simulation is one of the major applications of computers that we use in engineering, right? What do? We don't do explicitly programmed? No, we do exactly highly explicit program. We tell exactly the computer what to do, step by step. Nothing is we leave it to the computer to do it. We tell it in absolute detail what to do, right? However, machine learning is making computers to act without explicit program. It does it through an open computer algorithm and learning from data rather than, so you use the same code of, let's say, artificial neural network for multiple different problems, for all sorts of different problems. The difference is this open computer algorithm learns from the data that you provided, and it does what you need to do. So with that definition, artificial, and I'm going to talk about these three algorithms that I've been using for the 30 years, is one is neural networks. So artificial intelligence mimics human brain, mimics nature to solve complex and dynamic problems, right? That's the general definition. Now, specifically, what is artificial neural network? Artificial neural network as an algorithm of AI and machine learning it mimics human brain's information processing. It mimics neurons in the human brain for the learning process. That's how why you need to learn about neuroscience. It helps you to learn through pattern recognition by using data to train a series of open computer algorithms. How about fuzzy set theory? Fuzzy set theory doesn't mimic human neurons, it mimics human brain's logic. And the fact is that mimicking the multi-valued logic that our brain or human brain uses is what fuzzy set theory does. The key behind it is it avoids the two-valued logic, the Aristotelian logic, that it's yes, no, black, white, 0, 1, what we call digitals, these items. It's avoid limitation of two-valued logic to expand the potential to learn and make reasonable decision based on non-exact information, because you know that a lot of information and data that we have is not exact. And don't forget that, I mean, it's a fact that our brain does not use engineering data in order to detailed data in order to make decisions. When you're driving and you have to stop, and when you see that green light turn to yellow before turning to red, right? You don't have exact inches of feet and inches of your distance to it, but what you think is I'm close or I'm far away, I'm half close, half far away, and then you make a decision. It's not about exact detail data rather than the non-exact information and data. That's how our brain works. And finally, the last third one, I'm not saying these three is the only algorithm, this is the only algorithm that I have been using for the 30 years, is a genetic algorithm, which is an optimization through natural selection. It mimics Darwinian evolution theory for optimization purposes, and it finding solution and optimization complex problems through natural selection. So with that, if I move forward, when I teach my students, one of the things I tell them to, as an engineer, how can you judge that you have become an AI expert, AI and machine learning expert? Because in order to be able to use the correct version of this technology, in engineering, first and foremost, you must have engineering expertise. If for those people who don't have engineering expertise, but they're expert in AI and machine learning, they cannot solve engineering related problem through AI. We have so many examples of that, which is very, very sad, but it's very, very true. However, you must have the engineering expertise to be able using AI. However, you also need to become an expert in AI and machine learning. And the question what I share with my students is based on my experience, how can you judge that you became an expert in AI? My experience has been, in order to find out whether you are an expert in AI and machine learning, you will be finding that you have become incredibly interested in evolution, because human brain comes from the evolution. It makes you interested to go back to say how it happened. In neuroscience, if you don't know how neurons work, if you don't start working and dealing with how human neurons in our brain works, then AI makes you very interested in that. It makes you interested incredibly in philosophy. Why? Because it goes, I'm going to talk about it as we move forward. The engineering application of AI, it's a new application of AI, not the traditional engineering that we learn at the university, using mathematical equation to solve, to model physical phenomena. But our expertise that we have learned from engineering, then the philosophy, I strongly recommend go to Stanford website and their philosophy website, and they have a lot of articles about AI philosophy, and it's strongly important, and you must read it, and you find out that one thing you learn is that you will be solving engineering related problem in a different fashion that you've learned at the university as an engineer. But whatever you learn, the technique is going to be changed, but not the understanding of engineering. It's incredibly important. As we move forward, then of course, computer science, statistics, and biology become very, very important too. With that, let's talk about modeling physics using AI and machine learning. First and foremost, let me ask a question. Can human brain address physical phenomena? You know, the rocket trajectory that happens when they want to hit a location with a rocket. What do? Well, this is the equation. They want to know where this comes down, what the range is. They need to know the initial velocity and the angle, and they of course know the. So very simple. You can, not very simple, but it's an equation, right, to do that. So through throwing something to be caught by another person, pretty much the same thing, right? So the question is, does human brain solve this engineering approach, this mathematical equation, and then comes to a conclusion and tells the muscle where to move and lets you know where to move to catch it, where the range is? Well, the reality, that's not the case. This is not how human brain solves physics-based problem. So then how does human brain solve physics-based problem? Well, but it does it by observation. It does it by learning through training and to trial and error, and does a lot of training. It uses data. Data used by human brain is uncertain and is full of noise. There is no doubt about that. However, since AI mimics human brain, can it use data to solve physics-based problem? The same approach. The answer is definitely yes. And that is the approach of engineering application of artificial intelligence. AI and machine learning is when computers are used to mimic the human brain to solve the problem, right? Strengthening a specific set of patterns of synaptic connections in the part of the brain that is responsible for the specific action. That's what happens. How does it do that? It does it through observation, through collecting data, through trial and error, through discovering patterns and practice and get better and better as a function of time. It's called the training, right? So it's a paradigm shift in science and technology, artificial intelligence. Its objective is to use data to solve problems through observation, learning, mimicking, and control. And this process goes back and forth. This is the training that goes up and down, and back and forth. So for a physical phenomenon to be modeled, the data that is collected is sent to the artificial neural network and other applications. The data-driven model is done, and it's a process that always goes on to get better and better and so forth. So modeling physics using data rather than mathematical equation, that's another key thing. That once proven that physics can be modeled by artificial intelligence and machine learning using data. What does it mean? Well, it means that AI-based model of physical phenomena can be developed using real measured data. That's another key issue that there's a whole different topic we should talk about. I have written articles. If you're interested, I'll give you the links to it. It's called AI ethics. But what is the AI ethics in engineering? Because the key is that it can be developed using you shouldn't do that in engineering. You shouldn't generate data from mathematical equation in order to build an AI model. That's the major problem that a lot of people in engineering do. And that's literally identifies lack of full understanding of this technology. It is about real measured data, actual data. This would serve as an alternative to the traditional modeling of physical phenomena. So modeling physics using data rather than mathematical equation is a data-driven modeling by physical phenomena using AI and machine learning. That's the main difference of it has with mathematical equation that we've been using for centuries. Is AI application of engineering makes no assumption. It makes no interpretation. It makes no simplification. It makes no preconceived notion and no biases. That is actually the ethics of artificial intelligence in engineering, because as you know, the ethics of AI has the non-correct application of AI by a lot of companies creates sexism, it creates racism. How? It has to do with the data. Can it cause ethics issues in engineering? Yes. When you use mathematical equation to generate the data and combine it with actual data, then you make it do what you want to do rather than what it can do from the reality. Okay. I can go into the detail if you're interested in this. So engineering application of AI and machine learning. Are there major differences in how AI and machine learning is used to solve engineering versus non-engineering problems? Okay, remember I told you that a lot of people started in engineering, hiring people from non-engineering, without engineering expertise, and they learned that that's a very, very bad idea. I'm going to explain that. Since human must be educated in the university in order to gain engineering knowledge, then machine learning algorithms also needs to be educated for engineering related problem solving. The question is, can a 5-year-old solve engineering related problem? Absolutely not. Can a statistician solve engineering related problem? Absolutely not. Because if it's a statistician, why do you become an engineer? We have a statistician. You don't need to become an engineer, right? If that was the yes. So there are differences between engineering problems and non-engineering problems. In non-engineering problem, the only thing you require is general intelligence. For non-engineering problem, what you do not require or need is domain expertise. However, solving engineering problem requires domain expertise. Let me give you an example. This is image recognition, right? If you take all these pictures, millions of pictures such as that, and tell them, can you find out which one is a cat, which one is a dog? Okay, the image recognition can do that actually. These are cat and these are dog. But my question is, can a 5-year-old do that too? Of course they can. I'm not saying what image recognition with AI is doing is simple. Actually, a lot of time that you do it for general intelligence, it's even more complex than engineering. Don't get me wrong. But you do not need expertise in very specific ideas. You need general intelligence. Another example, face recognition, right? In face recognition, does your 5-year-old needs expertise to find out which one is dad, which one is mom, which one is sister, which one is brother? Object recognition. How much do you need? How much do you need to learn above and beyond? Do you need to go to university to find out which one is a car, which one is a bicycle, which one is a person, which one is a truck? How about voice recognition? Again, none of these are simple to do. Don't get me wrong. They're very, very, very hard to do, but it requires general intelligence. It doesn't need any expertise because a child can tell whether mom is calling me or dad. Is my brother talking to me? Is my sister talking to me? How about autonomous vehicle? Do you need a BS, an MS, or a PhD to drive a car? No, you can drive a car even if you cannot write or you can read. So general intelligence allows you to do that. Again, it's extremely complex for AI to do it, but it is general intelligence, right? Translation, same thing. A child can speak multiple language when he has a father from one country, dad from another, mom from another country, right? And caption generation, which LSTM, they made it for that. Again, can somebody says that, oh, this is a bird flying over water? Okay, so how about engineering application of that? Question. You have two types of dots. You have yellow and black, right? So if you ask a child to draw a line to separate yellow from black, can he or she do it? Of course, if it's a 5-year-old, just draw that. However, what if you tell that child or that person who doesn't know mathematics, say, dear, this is a nonlinear separation of these two. What I want you to do is linear separation. Then that person needs to know mathematics to be able to separate it through a linear separation. You see, if there are certain things you need, then you need certain expertise for that. So two major questions. When it comes to engineering problem solving, first, is general human level intelligence enough to solve engineering related problem? That's the first question. The second question, do humans need to learn anything to be able to solve engineering related problem? Let's find out. The first one, the answer is no. General human level intelligence is not enough to solve engineering related problem. It is engineering knowledge and domain expertise is a requirement. That's why you guys went and get a bachelor and master and a PhD and then go work and get experience. Therefore, domain expertise is a requirement for artificial intelligence to solve engineering related problem. How about learning? Yes, the learning of anything requires teaching to understand detail of engineering. Therefore, engineering characteristics must be taught to the machine learning algorithm through data. And if you want to make that teaching, you must be a domain expert. Does human brain build equations and then solve find a solution? No, as we showed you, the human brain uses its neurons through its dendrites through its axon and cell body and the connection of them through what's called synaptic connection for observation, experience, and trial. Anyway, let's move forward. I'm going to end this by telling you one thing and see why this technology is very interesting and how people think about it and deal with it. If you see this, I would like to know your opinion. What do you think if a company comes and say, we're going to make you master physicist in just 1 month? What do you think? What if another company in their marketing say, we're going to make a master chemical engineer in just 1 month, or a master mechanical engineer in just 1 month, or a master petroleum engineer in I just made this up. But the question that I have for you, does it make sense to you? Obviously not, right? Because this is not, what you see is not real. No company has ever done such marketing, because it just makes absolutely no sense. How about this one? Master data science in just 1 month. This is actual. This is a real marketing advertisement, folks, because they think data science takes very little for you to learn. But engineering? Anyways. So let's talk about AI and machine learning versus traditional statistics. Traditional statistics, the birth of statistics is often dated in 1662 when John Grant, along with William Petty, developed early statistical and census method, provided a framework for modern demographic. And the word statistics occurred in 1770. And Tom Bayes, the Bayesian statistics was named after him, who formulated the specific Bayes theorem in 1763. What is the statistical analysis? So the question is, after all these things I told you, why in centuries that statistic was there, it didn't do what AI has done in the past couple, 2-3 decades? Don't you think there's a difference? Statistical analysis, the thing that they're common, they're using data. But how? Using existing models. That's what statistics analysis do, to identify pattern in data. It matches predetermined patterns, linear regression, nonlinear regression for a specific shape of the equation. So it matches predetermined patterns to the data deductively, I'll explain that, following Aristotelian approach to the truth. And traditional statistics is all about correlation. How about AI? AI discovers existing pattern in the data to build the model. It doesn't compare it to the existing models. It discovers pattern in the data inductively, not deductively. I'll explain that in a minute. And it doesn't go through Aristotelian approach, it goes through Platonic approach to truth. And AI provides correlation as well as causation. That's why engineering application of AI is explainable AI. I will explain that. What is the difference between deductive and inductive reasoning? Deductive reasoning starts with a theory, that's a statistics, and it makes prediction and it comes to experiment, or compare that to the experiment. Inductive reasoning starts with observation and it comes up with generalization, and then it does a paradigm. Deductive reasoning, exactly the same thing, going to a little more detail, starts with the theory, confirms the hypothesis, arrives at conclusion. Inductive reasoning starts with data, infer conclusion from the data, and arrive at conjecture at conclusions or conjecture. Conjecture is conclusions formed on the basis of incomplete information. Because when you have information from have data from a specific, do you have everything that it requires? No, but you have hopefully enough to build the model. So if you go from general principle to specific cases, then you're using deductive reasoning, traditional statistics. And if you go from special cases to a general principle, then you're using inductive reasoning. And that is artificial intelligence, and it's different from statistics. Another example, a known function representing a reality, everything about something that is real. However, we have only data used for training. We have a certain amount of data to deal with that, not every data that exists. If we use that data and we use a set of hypotheses and identify which one of these hypotheses work with it, that's statistics. But if we use that data to learn an algorithm, and then what comes out of it, its final representative model of so many different equations combined, it's very, very hard to look at in detail. That's machine learning. So statistics versus machine learning is fitting data to predetermined equation versus discovering complex pattern in the existing data. These are the general items for each one of them. I'm not going to go into the detail of that. So the fact is, what is not AI and machine learning is logistic regression, linear regression, multi-val, and you can see all of that, but these are the artificial intelligence. But let me go ahead, and one thing we talked about causation and correlation. So when traditional statistical analysis are presented to engineers and scientists, one of the most contentious issues that is usually brought up is the relationship between correlation and causation. Engineers and scientists usually mention that correlation and causation are not necessarily the same. Is that true? Yes, it's correct. Here's an example. What you're looking at is for 10 years, comparing the data of US spending of money on science and space and technology, and compare it with suicide by hanging and so forth. They correlate 99.2%. Are they causing each other? How about divorce rate in state of Maine versus per capita consumption of margarine? 99.3% correlation. Are they causing each other? And finally, the US crude oil import from Norway versus drivers killed in collision with railway. So anyways, obviously correlation and causation is not the same. So with all that, there are two ways of applying AI in engineering. One, which I'm not covering here because the time, and because I have done it in petroleum engineering rather than the non-petroleum engineering, is when you use only data to build a physics-based model, not mathematical equation. However, a smart proxy model is the application of AI and machine learning to numerical simulation. The numerical simulation is done through complex mathematics and a very, very complex system. And I'm going to show you what smart proxy does. The time coming to end because I want to show you a case study. So I'm going to go just one here. The difference is the traditional proxy modeling uses mathematics and statistics, and they're known as reduced order model and response surface model. Smart proxy is the new one that uses AI. And the traditional proxy model, which is ROM and RSM, reduced order model and response surface model, they are used mathematics and statistics to do it, and they make a lot of changes. Actually, let me go quickly. And these are tells you when they were developed, who developed them, and how. And they make differences. So smart proxy modeling is a complete paradigm shift in how to build a proxy model of the numerical simulation. You have to it replicates the results of the original numerical simulation. It does it with very high accuracy, more than 95%. I'm going to show you examples. It does it at the grade block, at the cell version level. It's not taking pictures and doing image recognition, CNN, convolutional neural network, and it decreases the computational footprint in order for magnitude. Smart proxy model can have thousands of deployment in a short period of time, even on your laptop. Okay, so with that, the smart proxy model, unlike ROM, does not simplify the physics of the numerical simulation, and it does not reduces the number of cells and number of time that it does. And unlike RSM, response surface model, it doesn't use statistics, and it doesn't do curve fitting and so forth. So what does the smart proxy model do? It teaches engineering to the open computer algorithm using data from numerical simulation. Data from numerical simulation includes data that is used to build the model, and key part of it is feature generation that explains, like that, I mean teaching to the machine learning algorithm, explains the physics and numerical solution of the numerical simulation to the machine learning algorithm. It is impossible to do this feature generation, if you're not a domain expert in the development of the numerical simulation. So with that, let me go ahead and given the fact that, okay, by the way, if you're interested, a book I have written on a smart proxy model, application of AI machine learning in numerical simulation, and this is in October 22nd, sometime in October of this year, is going to be completed, the publication, and it goes to a lot of detail. But let me give you a case study. This case study has to do with a mechanical and chemical engineering CFD, computational fluid dynamics. It has to do with a boiler that is involved with complex production of manipulation of steam. There is water, there is heat, and of course, from a chemical reaction, you have air, fuel, and heat. And what do we do with the steam? Steam powers the turbine and is an efficient method. This is literally what the computational fluid dynamic has been done. They build it in NETL, National Energy Technology Laboratory of the US Department of Energy. It has three parts: a fuel system, air system, and water system. This is the fuel system part of it. This is the air system part of it. This is the water system part of it. And this is the computational fluid dynamic that they made with different areas. This is the general version of this, and it shows you the reheater, the superheater, the economizer, upper, the lower, and the reheat front, and so forth. And this is where at the bottom you can see the injection port, where the fluid and air comes in, coal actually, with air comes in to generate the heat. And of course, the cells that are used, there are tetrahedron, and it tells you primate and hexahedron. There are a total of 4 million, more than 4 million cells to build this system. If you're interested, I'm going to show you all of that detail, but let me go ahead and show you the results that we generated. So what we did, the NETL, National Energy Technology Laboratory of the US Department of Energy, created 32 CFD only. They gave it to us. We used 21 of those CFD deployment, to train and calibrate the model, the smart proxy model. And then we didn't use 11 of those deployment that was provided to us. We used overwhelming majority of that 11 as a blind validation, because the key is you have to show, if you keep everything generally the same, but you change other input, other stuff in the numerical simulation. For those of you who know, the key is how can you do it for optimization, for uncertainty quantification, for solving problems on different situations. You can literally run it, run new ones. So that's why we use blind validation. This 11 blind validation, these are the deployment that was not used to build the smart proxy. This was used in order to find out the smart proxy model that we develop is good or not. The CFD output that we did here was pressure, nitrogen, oxygen, carbon dioxide, and temperature. I'm going to show you very quick. What I'm going to show you is the blind validation only. There are two of the runs, run number 5 and 6 that was not used. And I'm going to show you the pressure distribution from CFD simulation and from smart proxy simulation. What this shows you is that the smart proxy that we developed, it shows you this is percent error, 2% error. So over almost 100% of all the cells have less than 2% error, actually less than 1% error. What I'm going to show you, this is the distribution, let's say in pressure, but I'm going to show it to you. We did it in 3D, but we're going to show it to you in this is 1, 2, 3, and 4 of them, and then compare them. So here is the first one. This is for one of the blind validation, run 5. This is the CFD model that NETL did. This is the smart proxy of exactly the same one. And this is the error. The maximum error, as you see, is 10%. And this is less than 2%. And I'm going to move these cross going forward. Proxy model versus NETL versus CFD and the error. This one, the third, CFD, proxy model and error. Fourth one. And now the same 4, I'm going to show you for pressure for another validation run. This is run number 6, again for 4 million. You get less than 2%. This is run number 6. It's a different run, as you can see. And on the left is CFD done by NETL. On the middle is smart proxy done at WVU, and the error. You subtract these two together in percentages, it's listed. So I'm going to move on forward. Go back again. Now let's look at nitrogen. Now for 6, this is another proxy model. I'm going to go back again for you. Now oxygen. For first one, for run number, blind validation number 5. For blind validation number 6. Now carbon dioxide for blind validation number 5. For blind validation number 6. Final temperature for blind validation number 5. For blind validation number 6. So literally it says that the percentage less than 2% error for during training and during blind validation, you can see the difference, which is very, very good. And keep one thing in mind. This was done a single CFD deployment that NETL would do on their HPC, incredibly fantastic HPC of US Department of Energy. It would take 24 hours for one simulation run, CFD. Smart proxy takes only a few minutes. You can do thousands of it in a couple of hours. Thank you very much. If there's any question, I'll be happy to answer.
You're welcome, Shahab. Thank you so much for the presentation. We're a little bit over time. So I will ask our next speakers, Jordan, if if Shahab can answer true or like one questions or true. Do you allow that? Because it's his time now.
Yeah, so I've enabled an extra time, so you can take maybe 5 to 7 minutes or so.
Okay, so for the attendees, if you have any questions, for Shahab, you can ask in the chat or like activate your mic and ask him directly. Thank you so much.
Let's see if there is any question that I can read from the top. Will AI be able to understand the intention of human-like pragmatic analysis? It all depends on the data that you use, how you approach. I'm not sure if I understand what that is. Anyways, any other question? Okay, that's always a great talk. Thank you. Fortunately, I have to drop. Okay, presentation. Okay, there is a question. You remarked in one of your speeches that last year that AI is a fashion that individuals in academia are adopting to show off. You still believe that way of thinking? Do you think that rather than being a specialized ability in computer science, AI is becoming a widespread and vital tool for next generation of students? Yeah, I have no doubt about that, actually. What I mentioned was that a lot of people use AI as a marketing technique rather than reality. That's what I meant. And my point was, as an engineer, you should literally learn what this technology is. And if you just know what data is and say, okay, I'm a data scientist, you know, that's, you saw people saying it takes 10 months to become a data scientist. So the thing is, we have to have a realistic understanding of what AI is and its application in engineering. Do AI solutions require less computational cost compared to? Oh, absolutely, a lot less, a lot less. As I said, 24 hours in HPC, few minutes in your laptop. Okay, thank you very much. In your opinion, what is the best way to integrate physics and AI? Do we start with, there is no integration. I don't call it integration. If you mean solving a physics-based problem using AI and you like to call it integration, is fine. But what you should not integrate is the data that is generated from mathematical equations that model the physical phenomenon with actual data that is measured from a physical phenomenon. That's what you shouldn't do. Why? Because the data that comes from mathematical equation that has been used to model physical phenomena. A mathematical equation, what does it show you? It shows you a pattern, a correlation between all the items that is inside that mathematical equation. When you generate data from mathematical equation, you're generating a pattern already. And if you put that pattern data that includes a pattern already, you put it into an AI, you always get good results, no doubt. But when you combine it with the actual data, you're literally telling it what to do. Hey data, hey AI, use this algorithm, this pattern that I just provided to you with the data. And if that doesn't work, don't do anything else. That's exactly when it's used outside of engineering. It's called ethics, because you can do that to incorporate sexism. You can incorporate racism in the data in that AI can learn and create sexism. Just read, please go to MIT. There is an institute there called AI Ethics in MIT, and they have done a lot of research to find out what Amazon, Google, IBM, they did, and it created sexism and racism. They didn't do it on purpose to do that, but it became sexism and racism. And then they did research, they found out why, then they stopped it and they tried to change it. The same companies. I'm not saying those companies are racist companies. No, they used the data. They didn't pay attention to the reality and the fact. Now it's going to change. It has been changing a lot. Okay, the opinion. In your opinion, what is the best way to integrate? Okay, that was it. Okay, last one. Which one is more to look into before dividing into application of AI and machine learning to solve engineering problem? Which one is more look into before? Okay, yes, which one is more looking into is definitely AI. And once you do that, you will learn that you have to learn statistics as well. It's a great technology, you have to learn it, but don't say statistics is AI and machine learning. Should we focus on learn more about data or implement neural net? Yes, it's all about data. You have to do a lot about data. You have to learn so much about what the data is. That's why your domain expertise becomes incredibly important. I think it's the end of it, or I don't know if I should go on.
Yes, thank you so much, Shahab, for this insightful presentation. And I will introduce our next session with Jordan Bernard. He will present empowering disabled access to work using the intelligent software. So without further ado, Jordan, you can activate your mic and camera and share your screen with the audience and start your presentation. Thank you so much.
Good afternoon. Can